Chemistry people, welcome to another edition of Learning Science at Home. So we are on to the ideal gas law, right? So ideal gas law is a really nice one. Everything up until now, Boyle's law, Charles' law, combined gas law, Gay-Lussac's law, have dealt with changes, right? So you take a balloon and you drag it to the bottom of the swimming pool where there's more pressure, or you take a balloon and you release it into the atmosphere where the temperature and the pressure change, right? All kinds of things can take place. But they've all dealt with changes, right? So the ideal gas law is going to be about one balloon. I've got this lung, and this lung is under this pressure, and it's this volume, and it's everything about one sample of gas. And the nice thing that it's going to add in for us is amount of gas, right? Nothing we've dealt with so far has dealt with how much gas, right? And in chemistry, of course, how much is, wait for it. You gotta wait. Do you know how we do how much? How much is it in chemistry? What do we use? I don't know if I have one sitting here. I do have one sitting here. It's moles, right? Oh, it's a one-eyed mole. I don't know. I think this was guacamole. He probably got showered with sodium exploding on him when we had that happen, right? So it's moles, right? So this adds in moles. So some keys to recognizing that you're dealing with an ideal gas law problem is, number one, you're not going to be seeing a gas undergoing a change. So it's not temperature and then this happened, right? It's not volume and then it's going to be all about one situation. And a lot of times we'll talk about amounts, either masses, because if you use a molar mass, then you can kind of mess with mass stuff there too, or amounts of gas. So that equation is right down here. That's this PV equals nRT. That is on the back of your periodic chart. I don't have a periodic chart handy, but pretend I'm holding one up and it's on the back of your periodic chart there. You should look and find that for some muscle memory. And we should jot down in some notes somewhere the 5 things that are in that equation. Pressure in atmospheres, volume in liters. N is as in number of moles. R as in 0.08206. Ugly units on that. Liters, atmospheres per mole Kelvin. It's a constant. And a lot of times with constants, you just throw whatever units you need on it so that things cancel out nicely. It's a laboratory generated value, right? You do a bunch of labs. In AP chemistry, we do that lab and we determine what that R value is, right? And then your temperature, and of course your temperature is in Kelvin because that's based on motion. Up until now, since you've been dealing with changes, it didn't matter if you were in atmospheres or millimeters of mercury or whatever. You just had to be the same. Right? So they cancel out. But now, since we have an R in atmospheres, your pressure has to be in atmospheres. Since your volume is in liters, your volume has to be in liters. So because R has certain units on it, our regular things need those units. You could look up a different R with different units, and that would be just fine. There's nothing magical about atmospheres. But since we're all using the same R value, let's use that. Your textbook actually uses a different one. They use a kilopascals and that kind of stuff. But this is the standard one that most colleges use and that kind of stuff. So if we're dealing with atmospheres and all that, we'll use this 0.08206. So let's try a problem here. If you have a 3.5 liter balloon that's at 0.89 atmospheres and room temperature, how many moles of gas do you have? So recognize there's nothing changing. We're not talking about multiple gases or anything. Dalton's law of partial pressures we'll get to next week. We're just asking about how much gas is there. And they gave you a volume, they gave you a pressure, they gave you a temperature. So you've got 3 of the 4 things, right, with that extra R, that extra gas constant. You got 3 of the 4 variables and the gas constant. So we do that. So just like with the other problems, make your list, number 1, right? So make your list. Oh, I better move this in case you're trying to reread that. Make your list. That gives you a chance to check your units. Are my units all good, right? So I have atmospheres, I have liters, I had Celsius. So you notice I added 273 to make that Kelvin. If you want to be 273.15, so you're all kinds of excited about that 0.15, feel free. I don't care about it, right? And then you've got your 0.08206 liters, atmospheres. So you've got everybody in here. Then you just take and you plug that into your equation. I've already rearranged this one, right? But you have your pressure. I'm pointing at things. Well, I keep pointing at things in all my videos. I have my pressure times my volume equals my over R and K, right? I'll go ahead and blow this up so you can kind of see how we rearrange that. Some people like to rearrange numbers. Some people like to rearrange variables. It doesn't really matter as long as we can get there, right? But if I do PV equals nRT, if I want this N by itself, I'm going to divide by R. That cancels out my R. I'm going to divide by T. That cancels out my T. So I have pressure volume over RT, right? And that's the same thing we've got there. So it's just basically dividing, right? Divide to get that thing by itself. So as we do that, I think I have an answer here on the screen somewhere. There we go. So that gives us 127 moles, and I left off the moles right there, so we'll just pretend that I've written moles there. When I was running through those, I did not write out moles. But if you look, your atmospheres are going to cancel out, your liters cancel out, you've got Kelvin under 2 bars here and Kelvin right here, and then you've got the moles under 2 bars. Well, if it's under 2 bars, right, then you multiply by the reciprocal. Remember learning that in junior high like 8,000 times, right? So that, since it's under 2 bars, it brings moles back up on top. All right, so let's look at another sample problem here. This one, why don't you try and solve this one, right, before you move on. So we'll read the question. 3.02 moles of oxygen at 700 millimeters of mercury and 100 Kelvin will occupy what volume? I would recommend you hit pause right now and try and solve this on your own, or at least get a step ahead of me, right? Make your list and then have me, here in a second, I'm going to do that. So here's your list. Hopefully, as you made your list, you recognize that there's a problem there. 700 millimeters of mercury is not going to cancel out. So we've got to change that to atmospheres, right? I'll show that one on the board real quick in case you're struggling with that. Hopefully you're not, but you've got 700. Notice there's a decimal point there, so you get 3 sig figs, 700 millimeters of mercury. And up from the back of your periodic chart, 760 millimeters of mercury is equal to 1 atmosphere. So multiply by the top, divide by the bottom, 700 times 1. Hopefully you can do that without a calculator, and then maybe you get a calculator to help you with this. Divide by 760. That was really small. Let me go ahead and blow that up so you can see that. Right, so you can get 700 times 1 atmosphere over 760 millimeters of mercury. So we can hopefully do that okay. And you're like, move on, that's not hard. Right? Hopefully you're like that, right? And then this is in moles, 3.02 moles, and 100 Kelvin. So everybody's got 3 sig figs, so we can keep 3 sig figs in our answer. So we just go ahead and my equations, PV equals nRT. The V is the thing I'm looking for. So with this one, I went ahead and plugged it in on here. So you see you've got your pressure times your volume equals your number of moles times R times Kelvin. So then I want to get V by itself. So if we want to get V by itself, we've got to divide both sides by the atmospheres, right? Look at that fancy animation. Look at me getting all tech savvy here, right? So divide both sides by 0.921. Now I've got moles on top, moles on bottom. Atmospheres on top, atmospheres on bottom. Liters, there's nobody to cancel with. Kelvin, that's a divide by bar there. Kelvin's on bottom and Kelvin's on top. So we're going to be left with liters. And when we do that, we get this 26.9 liters for our volume. If you see STP in a problem, remember that from earlier this year, that stands for standard temperature and pressure. So again, write it down somewhere where you're doing your stuff. Standard temperature is 273 Kelvin. That is not room temperature. Room temperature is 25-ish Celsius, except in this building, it's like 5 Celsius right now. But that's 0 Celsius, right? So standard temperature, somebody decided along the way that that would be 0 degrees Celsius. I don't know why, because nobody works in 0 degrees Celsius. But 0 degrees Celsius is our standard temperature, and 1 atmosphere is our standard pressure, which is pretty much room pressure, right? We're up a little bit from sea level, so it's a little lower, but not a whole lot. All right, hopefully that helps. Start working some of those problems out of the packet so that you're ready to go on those tomorrow.